everyone and welcome back to our channel. In today's video, we are going to dive into an interesting topic in material science, that is the temperature dependence of the electrical resistivity for normally conducting as well as superconducting materials. So let's break this down step by step. Okay. So here we have a graph that shows the variation of electrical resistivity with the temperature. On the y-axis, we have the electrical resistivity, which is a material's opposition to flow of electric current. And on the x-axis, we have temperature measured in Kelvin, starting from absolute 0. Notice the two curves, one represent a normal metal, this one is representing a normal metal, and the other one representing a superconductor. Let's first talk about the normal metal. So let's see the first one. For a normal metal, as the temperature decreases, so if you are moving like this, temperature decreases, okay, the electrical resistivity also gradually decreases. So you can see as we are moving down, so electrical resistivity is also decreasing. This happens because at lower temperature, if you go to lower temperature, right, the atoms in the metal will have less kinetic energy, so there will be less vibration, and that will reduce the scattering of electrons and allowing them to flow more freely within the metal. Okay. However, if the temperature is extremely low, okay, near absolute 0 like that, the resistivity is not becoming 0. It's not becoming 0, right? There is still a small residual resistivity due to we can say impurities or defect in the metal lattice, and as the temperature is high, the resistivity is high. Okay, now let's move to the superconductor, this graph, the top one. Okay, at higher temperature, the superconductor will behave just like a normal metal. You have the superconductor at higher temperature, it has high resistivity, right? Now, but something extraordinary happens as you decrease the temperature, okay, at the Tc, right, and below Tc, something extraordinary happens. What is that? As the temperature reaches this Tc, the critical value, right, that is marked Tc on the graph, the resistivity is suddenly dropping to 0, exactly 0. Okay, so this phenomena is known as superconductivity. It means that the material can conduct the electricity without any resistance at all. Okay, yeah. The temperature Tc is also called the critical temperature, is a defining characteristic of superconductor. Below this temperature, okay, the materials enters a superconducting state. This happens because the electron pair, okay, the electrons pair up to form, we call as Cooper pair, right? What we called it as Cooper pair. Okay, so as the electron will get paired up in the form of Cooper pair, then they can move easily through the lattice without the scattering. This pairing is a quantum mechanical effect and is key reason behind the zero resistivity, right? So if you compare the two curves, the key difference is clear. While normal metal always retain some resistance, while the superconductor is going to lose all the resistance below the critical temperature. This unique property makes superconductors incredibly useful in applications like magnetic levitation trains, here you can see maglev trains, and MRI machines, and even in quantum computing, right? Okay, so that's the story behind this graph. If you have any doubts, drop a comment below, okay, and if you have any suggestion also, okay. Thanks for watching, and we'll see you in next one. Thank you.